Yeah, students, welcome back to next session. In this session, we are going to see the temperature sensors. Temperature sensors. Temperature IC, thermistor, RTD, thermocouples, and the governing principles. Also, we are going to see here. So temperature sensors, temperature to see the temperature, a condition of a body by virtue of which heat is transferred to or from other body. So this is the temperature simple definition. Temperature is a fundamental unit like mass, length and time. So here temperature is measured degree Celsius or Kelvin or the degree Fahrenheit. For most widely used temperature detectors are thermocouples, RTDs, resistance temperature detectors, thermistors, bimetallic strips. So these are the four popular types of sensors. So thermocouples are most widely used temperature detectors in industry, and the working principle of thermocouple is based on thermo EMF. The three basic laws of thermo EMFs are: the first one is Seebeck effect, Peltier effect, and Thomson effect. These are the three effects based on this. These thermocouples are made or are developed. So first one is Seebeck effect. It is if two dissimilar metals or alloy wires A and B are joined together to form a loop, and a difference of temperature exists between the two ends. So here most importantly, two dissimilar metals. So when two dissimilar metals or wires, alloy wires A and B are joined together to form a loop, and a difference of temperature exists between the two ends. So this is the basic principle. A potential difference across the junction will set up, resulting in thermos electric EMF. So this is the very small EMF is produced. So the magnitude of this EMF will be dependent upon temperature difference between these two junctions and the materials used for two wires. So here this is the simple Seebeck effect demonstration. So this is cold junction T1, and this is voltmeter to measure EMF, and this is copper and constantan are made to join at junction 2. So this becomes a hard junction T2. So this is a reference junction, and this is the another junction where the temperature or the EMF is measured, temperature is generated. So this is the simple demonstration of Seebeck effect. Next is Peltier effect. It is very similar to Seebeck effect only, but a slight modification is done in Seebeck effect. When a electric current crosses a junction between two dissimilar metals, so it is the actually the EMF is generated in Seebeck effect, but the electric current when you made it to pass, so in reverse order it is defined to Seebeck effect. One junction get heated up and another will evolve the heat, that is cold junction. So it is a reversal of Seebeck effect. And next is Thomson effect. So if a conductor is subjected to a temperature gradient, then a corresponding voltage gradient will be generated along the conductor. The current will flow from cold junction to hot junction. So this is another way of defining the same concept by Thomson effect. So thermocouple construction, it consists of pair of dissimilar metal wires joining together at one end, forming the sensing or hot junctions. The and terminator at the other end as a reference or cold junction, which is maintained at a known constant temperature, that is known as reference temperature. When a temperature difference exists between the sensing junction and the reference junction, an EMF is produced. The magnitude of this voltage depends on the material used for the wires and the temperature difference between the two junctions. So here this is when the reference junction is terminated by a meter or recording instruments, the meter indication is proportional to the temperature difference between the hot junction and the reference junction. This thermoelectric effect caused the potentials at the junction is known as Seebeck effect. So this is again the demonstration of Seebeck effect only. So this is the thermocouple construction, and this is sensing junction, and this is the meter or recorder, and this becomes the reference junction. And the thermopile, it is another device to measure temperature. It is nothing but series of thermocouples connected together. So series, many number of thermocouples are connected to measure a very high temperature situation like that. So thermocouple materials, the metals including copper constantan, iron constantan, chromal constantan, chromal aluminum, platinum rhodium. These are the popular metals. They cover wide range of temperature going as high as 2700 degrees Celsius. Up to this high temperature, we can measure using these materials. So this is the graph. So the thermal EMF produced in terms of millivolts for different metals and metal combinations across its temperature in which is given in Fahrenheit. And here you can see the more thermal EMF is produced for chromal constantan combination of materials, and this is for iron constantan, copper constantan, platinum rhodium. So for these combinations the EMF is produced. For platinum rhodium, the EMF produced is very lesser when compared to chromal constantan. So this, from this graph we can infer this. So advantages of thermocouples, these are rugged in construction, comparatively cheap, temperature ranges between 250 degrees Celsius to 2500 degrees Celsius, easy calibration, good reproducibility, good accuracy, and bridge circuit for sensing is not required because output is available directly in the millivolts. So there is no bridge circuit is required like in strain gauges in load cell we have seen the Wheatstone bridge circuit, so similar circuit is not required here. So limitations of thermocouples, for accurate measurement of cold junction compensation is necessary. So cold junction compensation is necessary, and EMF versus temperature characteristic is non-linear. So except for few materials, approximately linear, and most of the material combinations shows non-linear characteristic only. So these are the limitations. Next, we'll see advantages and disadvantages of thermocouples. So very small voltage is obtained as output. There is a very small EMF. So that should be amplified or that should be processed in order to get the meaningful reading out of it. So resistance temperature detector, this is another type of temperature sensor. RTD is a very popular one when we compare the thermocouple. The change in temperature is detected by change in resistance of the wire, and there are two types of RTDs having positive and negative thermal coefficients of resistivity. Resistance increases or decreases with the increase in temperature respectively. RTDs are constructed using bridge circuits. The change in temperature causes considerable resistance change, which gives a voltage drop in accordance with the thermal coefficient of resistance of the wire. So there are two types. This voltage is further amplified and the temperature is read thus. So this is the bridge circuit. RTD is a unknown resistor, and R1, R2, R3 are known resistors in this Wheatstone bridge circuit. So advantages of RTD: linearity over wide range operating range, wide operating range, and higher temperature operation, better stability at a high temperature, and applications are it is widely used in furnaces for automatic temperature measurement, used in medical and chemical laboratories to detect very low temperatures like dry ice and liquid nitrogen. So disadvantages are low sensitivity. It can be affected by contact resistance, shock and vibration, requires no point sensing, higher cost than other temperature transducers, and these are the disadvantages of RTDs. So next, thermistors. Thermistors, it is also known as thermal resistor. A thermistor is a type of resistor whose resistance strongly depends on temperature. A thermistor is a temperature sensing element composed of sintered semiconductor material and sometimes mixture of metallic oxides such as manganese, nickel, cobalt, copper, and iron, which exhibits a large change in resistance proportional to a small change in temperature. Pure metals have positive temperature coefficient of resistance, alloys have nearly equal zero temperature coefficient of resistance, and semiconductors have negative temperature coefficient of resistance. So thermistors can be classified into two types. One is a positive temperature coefficient, that is PTC thermistor, and another one is NTC. So resistance increase with increase in temperature. Negative temperature coefficient is resistance decrease with increase in temperature. So that is NTC thermistor. So characteristics of thermistors. In NTC thermistor, the resistance decreases as the temperature increases according to the following expression. So RT equal to R naught E for beta 1 by T minus 1 by T naught, where RT is the resistance at temperature and R naught is the resistance at temperature T naught. T naught is the reference temperature, it is normally 25 degrees Celsius. Beta is the constant, its value is decided by the characteristic of material. If the value of beta is high, then the resistor temperature relationship will be very good. Then the sensitivity of the thermistor also increases. So this is NTC and PTC. So when resistance increases, the temperature decreases. So here, when the temperature increases, the resistance also increases. So that is NTC and PTC. So this is the reference temperature. So advantages of thermistors: they are simple and easy to weaving their small sizes. Their cost is low. They are highly sensitive. They can be adapted to various electrical readouts with the help of computers. Thermistors can be easily used for accurate temperature measurement. Disadvantages: the temperature versus resistance curves of thermistors are highly nonlinear, and it is not rugged and requires delicate handling, which limits its application. They are susceptible to self-heating errors. Their range is limited to few hundred degrees Celsius only. It is not suitable for a higher temperature measurement. Thermistors use semiconductor which are prone to permanent decalibration, and these are the advantages and disadvantages of thermistors. Applications of thermistors. Thermistors are used in automotive applications, instrumentation and communication, consumer electronics, food handling and processing, defense and aerospace. So next we have bimetallic strips. Bimetallic strips is another type of temperature measuring device. So it is used to convert temperature change into mechanical displacement and thus acts as a temperature sensor. The strip consists of two strips of different metals which expand at different rates as they are heated, usually steel and copper, because the temperature coefficient of these metals are different. So here you can see this when heated up, this is when this is passive side and this is active side. Strip bends when temperature changes, so flat bimetallic strip, and this is curved bimetallic strip, and this is a flat spiral bimetallic strip. So spiral type is also another configuration of bimetallic strip. This is helical bimetallic strip. This is helical type of bimetallic strip. So bimetallic thermometer, all metals change in dimension, that is expand or contract when there is a change in temperature. The rate at which the expansion or contraction takes place depending on the temperature coefficient of the expansion of the metal, and this temperature coefficient of expansion is different for different metals. Hence, the difference in thermal expansion rates is usually used to produce the deflections, which is proportional to the temperature changes. So here we can see K1 is the low expansion coefficient and K2 is the higher expansion coefficient. That's why it is bending like this on temperature difference. So this is T naught. T is lesser than T naught. So T is having T naught is the normal temperature. When T is lesser than T naught, then it bends like this. So this is how bimetallic thermometer works. So this deflection is directly proportional to the temperature. So this deflection can be measured using any other device like LVDT or some other measuring device. Bimetallic thermometer consists of bimetallic strip. The two metal strips are joined together by brazing, welding or riveting so that the relative motion between them is arrested. So there should not be any relative motion between those two strips. So if there is any relative motion, then you will not get the accurate measurement. Bimetallic strip is in the form of cantilever beam. It is in the form of cantilever beam always. An increase in temperature will result in the deflection of the free end, and the strip is shown in diagram earlier slide. So this deflection is linear and can be related to temperature change. The radius of the curvature of bimetallic strip, which was initially flat, is determined using the following relationship. So I will show you this equation. So R equal to T3 1 plus M also all square plus 1 plus Mn M square plus 1 by Mn divided by 6 alpha H minus alpha L T2 minus T1 1 plus M whole square. So this is a relation used in bimetallic strip where R is the radius of curvature at temperature T2. T is equal to total thickness of bimetallic strip T1 plus T2, and M is T1 by T2 thickness of lower expansion metal divided by thickness of higher expansion metal. So alpha L is coefficient of expansion of lower expansion metal and alpha H is coefficient of expansion of higher expansion metal. So T1 is initial temperature, T2 is the temperature, the actual temperature. So this is the relation in bimetallic strips. And then we have advantages of bimetallic thermometer. They are simple, robust, and inexpensive. Their accuracy is between plus or minus 2 percentage to 5% of the full scale range, and they can withstand 50% of over range in temperatures. They can be used wherever a mercury in glass thermometer is used. And disadvantages of bimetallic thermometer are They are not recommended for temperature above 400 degree Celsius. When regularly used, the bimetallic may permanently deform, so which will introduce errors also. So if you are using it regularly, it may tend to permanent deformation. Applications of bimetallic strips and thermometers. The bimetallic strip is used in control devices. The spiral strip is used in air conditioning thermostats. The helix strip is used for process applications such as refineries, oil burners, tire vulcanizers, etc. etc. Comparison of Thermocouple, RTD, and Thermistor, a chart I have prepared, and this is the small comparison, and this is the symbol of Thermocouple. So Thermocouple, and this is RTD, and this is Thermistor, and temperature, the sorry characteristic, how the voltage EMF is varied here, here, and here, and advantages I have segregated here. Disadvantages also I have segregated here, and I have already listed in those respective headings. So coming to the last type of temperature detector, it is IC temperature sensor. There are integrated chips directly available to measure temperature. An IC temperature sensor is a two-terminal integrated circuit temperature transducer that produces an output current proportional to absolute temperature. The sensor package is small with a low thermal mass and fast response time. The most common temperature range is 55 degrees to 150 degrees Celsius only. It is not used for higher temperature ranges. The solid state sensor output can be analog or digital. On circuit boards, to monitor and control temperature, on circuit boards, on PCB boards, to monitor temperature, this can be used. In computers, to control CPU temperature. In telecommunication applications, cell phones, and process devices. In some industrial immersion applications also, these are used. So strengths and weaknesses of IC sensors. There is analog or digital outputs available, low cost direct voltage current or digital output needing no additional circuitry here, because it is directly designed and measured. So the linear output, no curve fitting, direct reading of temperature 1200 degrees Celsius, and 298 Kelvin or 25 degrees Celsius on some analog devices. Various communication interfaces. Weaknesses are narrow temperature range. It is not used for most of the temperature measurements. Wide interchangeability than most RTDs and thermistors. Wide variation in accuracy between different models. Small package sizes can be a barrier to low cost applications in some immersion designs. So these are the challenges or weakness. So there ends the temperature sensors, and you can refer same AK Ghosh book, Instrumentation and Control by AK Ghosh. That is a very good book. Apart from that, we can refer our regular textbooks and reference books. So there ends the temperature measurement. We stop here. We will again meet in next session with a new topic. Thank you, students.